All right, thank you. I'm Joey. I'm a software engineer at Kavala, and today I'm going to talk about how we're using Ray for large-scale time series energy forecasting. To give a quick overview of what I'll be talking about, I'll start by giving some background on energy forecasting, and then I'll talk about Kavala's approach specifically here. I'll talk about some of the key technical challenges we've faced, as well as how Ray has been really helpful for us. Then I'll talk about some ways we've optimized our time series storage. And then finally, I'll talk about what it's been like deploying and running all this in production. So jumping into that background, I'll start off with an overview of what Kavala is. So we are an electric grid intelligence platform. We work with customers who are interested in data around the power grid. And so this includes utilities, regulators, renewable energy developers, and transportation planners. And for these customers, we serve a variety of different use cases. These include things like power distribution planning, which is what I'll focus on today. But we also serve use cases around site selection for renewable energy developments, carbon accounting at a macroscopic grid level, power flow simulation, and analysis of utility rate structures. So starting with a background on power distribution planning, the goal of this process is to plan all the infrastructure needed to deliver electricity to end customers. So there's a number of different pieces of equipment in this flow. Power will start off at some sort of power generating station. It'll be stepped up to a transmission voltage where it can flow across large transmission lines. Then as it gets closer to end customers, it'll go to an electrical substation where it gets stepped down via substation transformers. These will step the power down to a distribution voltage where it can flow across smaller distribution lines. And finally, once it's very close to the end customer, it'll go through another transformer where it's stepped down to the voltage the end customer needs. And so all of these pieces of equipment need to be carefully planned to ensure safety, reliability, and affordability. Every single piece of equipment here has some sort of capacity where if the electricity at any point goes over that capacity, you'll get an overload, which is very bad. Not only will this cause blackouts, but this also can damage expensive equipment, or in the worst case, start fires. In California, we've had quite a few large wildfires that were a result of electrical equipment. Recently, this planning process has become even more complicated because we have all these exciting new technologies like renewable energy, like solar and wind, as well as electric vehicles and battery technology, which are all awesome because they don't emit any carbon, but they're more challenging because they're distributed and time varying. So, like I said, these are difficult to plan because the time series behavior varies for the hour of the day or the day of the week or season of the year, both in the generation or consumption of these technologies. So you need to consider the full time series when planning these out. And then these technologies are also distributed rather than centrally planned, and you don't necessarily know where all of these are going to end up on the grid, which again makes planning more difficult. Despite all that, it's still really important to plan this because climate change is happening really fast, so we need all these technologies. And also, the current interconnection processes for these technologies are quite slow, especially around electric vehicle charging stations. Sometimes this can take many years to connect a new charging station to the grid. Kavala takes a new approach to all this by doing bottom-up forecasting, which means we forecast energy at the level of individual electrical customers to predict their time series energy behavior and which technologies they will adopt. This has multiple benefits, but one of the big benefits is that you can account for more geographic and building-specific input features. You can also more precisely model the time-varying behavior of these different energy technologies. And you also it also allows for more sophisticated follow-up analysis like power flow analysis and rates analysis. One of our earlier proof points of this technology was this report we did for the California Public Utilities Commission, where we ran bottom-up forecasting across all of California to predict the impacts, particularly of electric vehicles, but also some of these other technologies. And this bottom-up forecasting let us predict much more granular and detailed output, from which we were able to predict that without taking certain mitigating steps, California's electric vehicle targets could cost the state up to $50 billion in grid upgrades in order to support those electric vehicle targets. So now I'll talk about what our forecasting pipeline actually looks like. So we'll take in a variety of different types of inputs, the first of which is just general building characteristics, like whether it's commercial or residential, the square footage, tons of other features like that. We also will take in the historical energy usage of that building if we know it. If not, we'll use a simulated version. And then we also use these top-down targets, which are a really important part of how utilities and regulators tend to plan, because they're often working with mandates that may have come from other parts of the government, and their goal is to make sure that they're going to be able to fit a certain amount of either renewable energy or electric vehicles by a certain year. And so from these inputs, we'll predict the technologies that might be adopted at specific buildings. This can include the specific types of renewable energy and capacities or a specific electric vehicle. And we'll also predict the future energy usage of each of those buildings. And the goal here is not to get 100% accuracy, because that's certainly not possible. But the goal is to create a representative scenario that can be used for planning purposes to identify problem areas and do more detailed geographic analysis of what the impacts are of these targets. There's a few big challenges in this pipeline. The first is that there's a lot of interdependencies between the individual tasks and predictions in this workflow. So the first type of interdependency is temporal dependencies. Those are pretty straightforward. This just means that, for example, if we're trying to determine the behavior of some building in 2030, we need to know whether we were predicting that they would buy an electric vehicle in 2026. We also have dependencies between these different technologies. For example, if someone buys an electric vehicle, that'll increase their overall energy usage and then make them more likely to purchase a residential solar system later on. And then because of these top-down targets I was mentioning earlier, we also have geographic dependencies where we can't just predict which technologies would be adopted at buildings with just a simple yes or no. We need to score their likelihood and then weigh them against all the other buildings in the geographic area to make sure we're meeting these top-down targets we have for each year. And the second challenge is the scale of data. Time series data can get very big, especially when you have geospatial components as well. So for us, we're running these, in the largest forecasts, we're running predictions over millions of buildings, for each of these generating hourly time series data per building over 10 or more years. And so this can end up being trillions of data points or terabytes of data. And so at these scales, data transfer can become a major bottleneck. So you really need to pay attention to things like data locality and caching, making sure you have optimized storage, and making sure your read and write processes are efficient. So Ray helps in a bunch of ways. In particular, we leverage Ray actors to run this workflow, and that gives us a lot of flexibility and scalability. So some of the big strengths of Ray actors are that they're highly scalable. You can scale them up to thousands or even tens of thousands or potentially hundreds of thousands of workers. They're also very flexible, since they're basically like writing a normal Python class. So you can write arbitrary Python code and run whatever types of models you want in them. They also can communicate fast with each other, which is really important for the different interdependencies we have. And then, in addition, since they're stateful, you can intelligently cache certain types of data in these actors that are relevant for your workflow. So for this forecast workflow specifically, we have two different types of actors. The first is a forecast manager. This is going to be what's managing the overall job flow. It'll also spawn a bunch of child actors to do the actual work. And it'll also run some amount of centralized computations, ideally as little as possible, because we don't want to be centrally bottlenecked, but some of these are pretty required for the workflow. And then we'll also have these batch forecaster actors. So each of these, all of these will do like the bulk of the actual work, and they'll be responsible for predicting behavior for batches of buildings in the forecast. And they'll also be able to cache data throughout the life cycle. To show how these actors work together, I'll walk through what 1 year of our forecast workflow looks like. So we'll start off with the forecast manager triggering the start of forecasting a particular year. Then we'll fan out to all the batch forecaster actors. In this case, these will predict the electric vehicle adoption likelihood for all the buildings they're responsible for. Those predictions will all happen in parallel. Once that's done, these results will then be returned back to the forecast manager, which is able to run a central process to assign which buildings actually adopt electric vehicles in this scenario. Then that information will be propagated back to the batch forecasters. And then we'll move on to the next technology in the workflow. In this case, it's solar. So we'll predict the solar adoption likelihood in parallel. Then once that's done, we'll collect those results back to the forecast manager again. And then we can repeat the process for any other technologies in the workflow. So next we've got batteries. There's also a bunch of other technologies not listed here that might be relevant. Some of these include energy efficiency upgrades or building electrification upgrades like heat pumps, as well as demand response programs. And the point of doing all of these sequentially is that we want to be able to use the outputs from previous steps as inputs into later steps, because like I was mentioning earlier, these technologies all influence each other. So for example, buying an electric vehicle means more likely to buy a solar system because you have higher energy savings. Then all of that can influence whether it actually makes sense for this building to purchase a battery system, because that really is going to take all the different types of energy usage into account and smooth out that underlying curve. And then as well, there's also, in all of these steps, there's a lot of time series input and output, which makes kind of the data challenges very important. Eventually, we'll have that final result, and then we'll be able to write that output in parallel from all those batch forecaster actors. So this shows what the actor code will end up looking like for our forecast manager. So many of you have probably worked with Ray actors, and they do look like regular Python classes. They're decorated with ray.remote, which is what indicates it's a Ray actor. And so when this forecast manager initializes, it'll spin up all the child batch forecasters that are going to do the actual work. And then once we're ready to run 1 year of the forecast, it'll call predict electric vehicle likelihoods.remote on those batch forecaster actors so that they can do the work to make their predictions. That summary will be returned, and the forecast manager will collect those results with ray.get into this electric vehicle likelihoods variable. Then it'll run the central assignment process to assign which buildings actually adopt electric vehicles, matching those top-down targets we had. And then we'll loop back over the batch forecasters and call update electric vehicle assignments.remote on each of them to propagate those assignments out. And then we can repeat this process for all the other technologies we're forecasting, and eventually repeat for any future years in the forecast. Then this shows what the batch forecaster code looks like. And one of the important things going on here is that certain data is cached that's going to be relevant through the life cycle of the forecast. And this is because each batch forecaster will be responsible for a specific set of buildings that it'll interact with over the full life of the forecast. So when this actor initializes, it'll retrieve all the input data that's relevant to those buildings it's responsible, cache that in local memory. And this includes building features as well as time series behavior. So this can be pretty big and take a significant amount of time for this initialization step. But once we've done it, we'll have it for the rest of the forecast. So eventually, the forecast manager will call predict electric vehicle likelihood on each of these actors. These will run the predictions using whatever model they want to use. And once they have those results, they'll update the results in that cache and then return a summary of those predictions to the forecast manager, which then will do the central assignments and then call update electric vehicle assignments on this actor, where it'll be able to update its internal cache with that assignment. Then, like I said, the rest of the technologies will be predicted, and eventually we'll be done forecasting that specific year. So the forecast manager will call finalize year on this actor, and then it'll write all its final output behavior to our persistent storage, and then it'll clear any temporary data that it only needed for that year so that we can make room for future years in the forecast. Now I'll talk a bit about how we've optimized our time series storage format. So when you're doing batch forecast or batch processing, there are a lot of considerations that can be pretty different from real-time time series usage. And so what that ends up meaning is that time series databases are not very well suited for these batch processing workflows. So instead, it's much better to store all your data in your cloud object store, because this is going to be much more scalable to whatever needs. If you have thousands of workers running in parallel, you're going to have trouble with all those trying to read from a time series database. So your object store is going to be more scalable. And Parquet files in particular end up being a good choice because they compress well, and any kind of data tools you'll want to use are going to operate well with them. But it's a challenge that you still have is figuring out how to align your file structure to all your usage patterns. So at Kavala, we have a few different usage patterns. One of these is retrieving data for a single building over time. This is kind of your classic time series usage pattern, nothing special here. But the other one that we have that's a little more tricky to handle is that it's also important for us to be able to retrieve data for an entire geographic region for a single instant in time. This ends up being really important for things like power flow simulation, where you need to know the energy load on an entire circuit in order to solve electrical engineering equations and figure out what equipment might have been overloaded at that particular time. So we want to make sure we can serve this use case as well with our time series storage. And then we also have the batch processing workflow, which is what I've been describing here. And some of the big needs here are making sure that you can read and write large amounts of data in bulk. And so ideally, we'd end up with a way of storing all our time series data that would serve all these use cases at once. So our solution was to use Parquet files and break them up into chunks that are partitioned by both space and time. For the spatial partition, we use census block groups, which are a geographic division that's created by the US Census Bureau. And what's great about these for our use case is they're adjusted for the density of different regions. So each census block group has somewhere between 500 and 3,000 people living in it. And you can see in this map of San Francisco, this shows what the census block groups look like there. And you can see that it's adjusted for density, with the block groups being much smaller in some of the more densely populated regions. And for our time partition, we use the quarter of the year. And these partitions together mean that we can serve all the different use cases I described on the previous slide, and we end up with chunks that are all around 5 megabytes in size, which is a pretty good chunk size for making sure that we're going to be able to retrieve small bits of information efficiently For example, if we're just displaying it to an end user on our platform, we want that to be low latency. And we're also going to end up with not too many small files. So this ends up being a good balance to serve all our different use cases. So we turn this into a high partition file structure, which is going to make it work very well with a lot of different data tools. And you can see this file structure matches what I was describing on the previous slide, where we first have our census block group partition, then our year partition, then quarter, and then we have one Parquet file in each partition. And so finally, I wanted to talk a little bit about what it's been like deploying and running all this in production. So this diagram shows what our overall architecture looks like. So we deploy on KubeRay, and that's been great because it makes it able to run it in our regular Kubernetes environment, and also gives us auto-scaling out of the box that works really well. So the workflow for actually triggering a forecast involves a user configuring and triggering the forecast through our forecasting service. This will then be able to call into Ray serve. There we'll spin up a forecast manager actor, and that will in turn spin up any batch forecasters it's going to need to run the forecast. These will all be run in an auto-scaling worker pool. If it's a small forecast, it might be able to run just on existing nodes. But if it's a larger forecast, the autoscaler will kick in, which usually is pretty fast, within 5 minutes, which for a large forecast, we'd probably be expecting around 2 hours for it to run anyway, so that's not at all a big deal to have to wait for the autoscaler. Then the forecast will run, throughout which it'll be interacting with different services we have. It'll do most of its reading and writing to Google Cloud Storage, but we'll also do some reading from BigQuery. And then eventually, once the forecast is finished, it'll signal the job completion to our notification service, which will then in turn notify the user that their forecast is done and ready to look at the results for. And so some of the stuff we've been able to achieve with this workflow is to run pretty large scale forecasts. So the largest one we've run so far predicted 10 years of behavior for 4 million buildings, running across over 1,000 CPU cores, using almost 5 terabytes collectively of memory. This ended up with about 1 trillion output points and to a little over 2 terabytes of output data. You can see the Ray dashboard from when this was running. One of the things to note here is that we were able to, by intelligently controlling what data gets cached where, we were able to get pretty high memory utilization, which is really nice because this helped us avoid a lot of unnecessary data shuffling, since all this data was able to stay in memory through the whole forecast. And then lastly, I wanted to wrap up by circling back to why these forecasts matter. Grid upgrades are critical to the renewable energy transition and moving away from fossil fuels. And with better planning, we can greatly reduce the costs of this grid upgrades. We can speed up the interconnection processes for electric vehicles and renewable energy. And while we're at it, we can also improve safety and reduce power outages. So thanks for listening. I'm happy to answer any questions.
Please raise your hand if you have questions.
How frequently would you be needing to retrain the forecasting model?
Yeah, that's a great question. So I'm not one of our data scientists, so that question would be better to ask our data scientists. So far, we do retrain our models. It kind of depends on the needs of the customer and the projects we're working on. So far, a lot of our models have been kind of custom developed depending on the needs of clients, and we'll retrain them when we have new engagements with those clients. But I think that's subject to change, so we'll see.
Any other questions?
What did you use before Ray? Did you have a different platform?
Yeah, so we had, it was a mix of things. We had a somewhat like internally built system that mainly leveraged Kubernetes pods, just like, yeah, raw Kubernetes pods. And the downsides of this were it was had more maintenance work for ourselves, and it also was less flexible and powerful in terms of using different kinds of workflows and making sure that you can, having the different jobs be able to communicate with each other. So it meant more, it was broken up into more steps where after certain parts of the workflow, you just write some persistent storage, and then the next tasks would have to read that data out. And so it was much more of a sequential, broken up process.
Hi, thanks for the talk. I would be interested to listen more about your model repository maintenance. You mentioned about actors, Ray actors. So how do you maintain the models across the actors, or is it the same model running on all the actors? Would you please expand on that?
Yeah, so the specific models that will be used, and each forecast will use a set of different models, generally different models for each technology that's being predicted, and even within there, there's those stages of the prediction are broken up into predicting, for example, the size of the size and type of the technology that would be adopted. Then we have models for predicting scoring that likelihood after that we've predicted the type, and then the behavior in terms of the time series behavior also needs to be predicted. So those all are separate models, and the types of models can vary a lot. In terms of like a model repository, so far I think we have some work to do in terms of making it a more consistent repository, but right now we have our models there's a lot of heterogeneity in how our models are written and where they're stored, and a lot of them are just written as, after they're trained, they're stored as sometimes pickle files, sometimes other formats in Google Cloud Storage.
All right, another round of applause for Joey. Thank you very much.